The last conversion that we need to do is between hexadecimal and binary. And we're going to find out that there's a symbiotic relationship that exists between hexadecimal and binary. The reason is there are 16 digits in the hexadecimal numbering system. That means that with one hexadecimal bit, I can represent the values between 0 and 15. That in the binary numbering system, if I have 4 binary bits, I can also represent the numbers between 0 and 15. If all 4 of the numbers are 0, that is a decimal 0. If all 4 of the numbers are 1, that is a decimal 15. So with 4 binary bits, I can represent 0 to 15, and with one single hexadecimal bit, I can also represent the numbers between 0 and 15. Let's talk about some vocabulary for just a minute. If I have just one of them, it's called a bit. If I have 8 of them, do you know what 8 binary or 8 decimal bits are? 8 of them are called a byte. You're probably familiar with your gigabyte or your megabyte download speeds on your internet. What do you think 4 of them are called? And what do you think that they have called 4 binary bits? There's actually a name. And the word for that is nibble. I am not joking. 4 bits are called a nibble. And so if there was one word that I would use to describe the conversion between binary and hexadecimal, it would be nibble. So let's do some conversion. We're going to start the conversion going from binary to hexadecimal. So let's start with a binary number and see how we can convert it to hexadecimal. As I said before, I have a tendency to put a hint of a space between the groups of 4. That's because groups of 4 are called nibbles. So starting with the least significant digit, moving to the left to the more significant digits, I am going to group my binary number by nibble. So I have 2 nibbles or 2 groups here. Under each one of the nibbles, I'm going to lay out some positional values. If you don't mind, I'm going to skip the exponents, the base and the exponents, and go directly to its original value. Each one of the nibbles is going to be converted separately. That means I'm going to have values 1, 2, 4, and 8 listed under each one of the individual nibbles. I'm going to take its positional value and I'm going to multiply it by the value that is sitting there, but we're going to do this for each one of the 2 nibbles. And so this is going to be 1 times 0, this will be 2 times 0, this will be 4 times 1, and then I'm probably going to have to put the 8 times 1 down here. So this is going to be 8 plus 4. This will be 12. Let me put the 12 down here. I'm going to do the same thing over here. This is going to be 1 times 1, and then I see a 2 times 1. I see a 0 times 4. I think I reversed that. And then I have an 8 times 1. Ultimately, this is going to be an 8 plus a 2 plus a 1. This number is going to be 11. And so this nibble is equivalent to 11. This nibble is equivalent to 12, and if I convert these 2 values into hexadecimal digits, because 11 is not a hexadecimal number, this is B and this is C. So we are going to see that the binary value 10111100 converts to a hexadecimal BC. So let's do another one. Remember, I am going from binary to hexadecimal. So let's do a little bit longer one. I'm going to group them by nibbles, and as always, I am going to start on the least significant digit, and we're going to work our way to the left to the most significant digit. I am going to group them by nibbles, and then I'm going to convert each one of the nibbles. So each one of the nibbles will have 4 binary positional values, and then we're going to see if we can convert this. Now, one of the shortcuts is that first nibble right here, there is a 1 only in one's place. If this is 1, 2, 4, and 8, the only value here is 2. If I repeat it, 1, 2, 4, and 8, the only values that I can see here are these 2 positional values, which fall under 2 and 1. So I can add 2 plus 1. I can see that there are 1s in the first 3. And so if I remember 1, 2, 4, and 8, that means we have 8 plus 4 plus 2. And then this leftmost binary nibble has a 1 in the first place and the last place. If that is 1, 2, 4, and 8, I'm going to add an 8 plus a 1. So this is 9. This is 14. This is 3. And this is 2. But we know that 14 is not a binary value. It is actually a hexadecimal E. And so this is going to convert into a 9, E, 3, 2 in hexadecimal. We are going to do one more. This one will be a little bit different. I'm going to put 110, 110. Once again, as I've said, we start with the least significant digit, and then moving to the more significant digit, we are going to group it by fours, by nibbles. Now, if I do that, that means this is the ending of the first nibble. And then we have these 2 left here that are just 2 out of the next nibble. What I can do is I can add leading ones to them if it's necessary. We will convert each one of the 2 nibbles. The only 2 that I need to be concerned with, because there are 1s in those positional values, are the 4 and the 2. The same thing on the other side. The only 2 that I need to be concerned with are the 2 and the 1. So this is a 3 and this is a 6. So the hexadecimal number is 36. Now, the reason why I wanted to do this one is because what happens if we group it differently? What happens when I write this 110, 110? If you see a 6-digit binary number and you say to yourself, we're used to moving left to right, what would happen if you were to group it from left to the right? Well, I have a binary nibble here, but there's only 2. So what am I supposed to do about that? Some of you might say, well, I'm going to add a couple of trailing zeros, and then I will convert those numbers. Some of you said trailing zeros matter. I remember she calculated my paycheck. So trailing zeros matter, but leading zeros don't matter. So what I'm going to do is I'm going to change this from, I'll put in some leading zeros because she told me leading zeros don't matter. So this value is going to convert to, we're going to have a 1, 2, a 4, and an 8. So once again, this is going to be an 8 plus a 4 plus, well, I see that there is a 1. So this is equivalent to a 13. This one, if I decide to tack on some leading zeros, because the instructor told me leading zeros don't matter, this is going to be 1, 2, 4, and 8, which means this will be a 2. So I'm going to have a 13. I'm going to have a 2. Well, I'm pretty sure that 13 is not a hexadecimal number. This is going to be a C, and this is going to be a 2. Well, we can see that these 2 numbers don't match up. If I had chosen to just convert the 2 instead of tacking on some leading zeros right smack in the middle of my number, this is going to be a 1, this is going to be a 2, that means that I have a 2, this is still a 2, a C2. So it is critically important that when you write your binary number down and you start to group the nibbles, that you always group starting on the right, the least significant digit, and then group to the left. So this is a binary number, and I want you to convert it to hexadecimal. Well, hopefully when you grouped your nibbles together, you started at the least most significant digit and you grouped to the more significant digit. Hopefully you came up with this grouping of nibbles. If you did that, you should have gotten a 30D in hexadecimal. So the last conversion that we're going to do is this time we're going to go from hexadecimal to binary. So I'm going to start with a hexadecimal number and I'm going to see if I can convert it to binary. So let's start with this number, A15. Remember, there's a symbiotic relationship between a single hexadecimal number and 4 binary bits, or a binary nibble. So if you don't mind, I'm going to space this out just a little bit to give myself some room, because each one of these hexadecimal digits is going to convert to a single binary value. So it doesn't matter which way I convert them or which order that I convert them, just so long as each hexadecimal digit equates to 4 binary bits. So the 5, if this is 1, 2, 4, and 8, I need to find some combination of these numbers that equals 5. Well, I'm pretty sure 4 plus 1 is 5. That means that the other two will be 0. If this is also 1, 2, 4, and 8, I only need a 1. That means the others can be 0. Well, my decimal brain tells me that an A is a 10. If this is 1, 2, 4, and 8, I need some combination that equals 10. 8 and 2 equals 10. That means that the others are going to be 0. So we're going to see that the hexadecimal value of A15 is equivalent to the binary 1010, 0001, 0101. So we'll do another one. How about if we do B, F, C, 2. So I'm going to start with them spread out just a little bit so I can draw the individual positional values below each one of the hex digit. All right, so we can start with a B or we can start with a 2. It doesn't matter which side we start on as long as we convert each one into a nibble. So in order to get a 2, I just need a 1 in the 2's place. The rest of them can be 0. A C is a decimal 12. How do I get a 12? I'm pretty sure 8 plus 4 is 12. That means the other two digits or the other two positional values will be 0. Pretty sure that an F is a decimal 15, and that is going to require 1s in all of the positional values. And then a B is a decimal 11. How do I get 11? 8, 2, and 1 is 11. And then I'll put a 0 in everything else. Now, remember, embedded zeros matter. And so at this leastmost nibble 2, these embedded zeros matter. I can't just drop them because there is nothing there. I have to include them. That a hexadecimal A15 is equivalent to a 16-bit binary number. All right, so I'm going to give you a hexadecimal number, and I want you to convert it to binary. Number is D29F. So if your answer is 1101, 0010, 1001, 1111, this 16-bit binary number, you got it right.